Nikki. I'm Sarah.
I'm Carmela.
And our product is derivatives, velocity, position, and acceleration.
Hey calculus buddies! Today we are going to try to incorporate derivatives and other subjects.
You may not know this, but position, velocity, and acceleration are all actually connected together. How? Derivatives.
Prepare to be mind-blown by how helpful this will be for your physics class and even your calculus class.
So our objectives today will go as follows. We're going to be understanding the difference between position, velocity, and acceleration. We will go over the application of first and second derivative, changing particle directions, and finding the minimum and maximum value of velocity. We will also cover acceleration and observe the relationship between velocity and acceleration in finding speed.
So let's focus on our first and second objective. Before we apply derivatives, we must be able to understand what position, velocity, and acceleration are and the relationship between them.
By definition, the position function defines the displacement of an object which is moving in respect to time. The velocity would be the rate at which that position function is changing with respect to time, and the acceleration would be the rate at which the velocity function is changing, aka the change in velocity.
So what's all this talk about rate? Moving on to our second objective, well, if you remember the definition of derivative, the derivative is the instantaneous rate of change of a function with respect to one of its variables. If you had noticed, position, acceleration, and velocity are all in respect with time. Not only that, but they are all connected by some rate of change. So if you hadn't guessed already, position, velocity, and acceleration are all connected by derivatives.
Because velocity is the rate of change of the position function, it is also the derivative of the position function. So if s of t is a given position function, the derivative of s of t is equivalent to the velocity function. The derivative of s of t equals v of t. We also went over that acceleration is the rate of change of the velocity function, which says that the acceleration function is the derivative of the velocity function, given that the second derivative of s of t equals a of t, or the first derivative of v of t equals a of t.
Let's go over an example.
Go.
So you're given your position function, which is s of t. So in order to find the velocity, all you have to do is derive s of t, which would give you s prime t is equal to v of t, which is 6x to the 5th minus 20x to the 4th minus 15x squared. And in order to find your acceleration, all you have to do is derive your velocity equation. So it would be v prime of t is equal to a of t, which is equal to 30x to the 4th minus 80x to the 3rd minus 30x. So our next objective is to find when a particle changes direction. A particle changes direction when the velocity reaches zero at the moment before heading in a different direction, meaning that it either goes from positive to negative velocity or negative to positive velocity, hitting zero before the direction change. The way to solve these questions is to see where the velocity function is equal to zero and if there is a sign change or not. Here is an example.
So in this question, we're given the position function cosine 3t minus sine 4t, and it asks us to find all the times the particle changes direction on the interval 0 to t to 2. So since we're given the position function, when a particle changes direction, it's actually when the slope changes. But for me, I feel that the easier way to solve this question is to find the derivative of the position function, the velocity function, and put that equal to 0 and find the points where t is equal to 0, because that's when it goes from either positive to negative or negative to positive. So I'll show you. So the first step would be to find the derivative of the position function. So s prime of t, which is equal to v of t, would be equal to the derivative of cosine 3t, which would be negative sine 3t times by the inside, which would just be 3, minus the derivative of sine, which would be cosine times by 4t, cosine 4t, times by the derivative of the inside, which would be 4. You just put this equal to 0. So 0 equals -3 sine 3t minus 4 cosine 4t. Now, if you put this equal to 0 and you graph it, you should get something that looks like this. So you can see here that the velocity function goes to 0 at 3 points. This point, and this point. So from here, it changes its direction from negative to positive. Here, it changes its direction from positive to negative. And here, it changes its direction from negative to positive. So on the interval from 0 to 2, the velocity reaches 0 at x is approximately 0.5978, x is approximately 1.3254, and x is approximately 1.8162. And it changes direction at each of these points. For 0.5978, it goes from negative to positive. From 1.3254, it goes from positive to negative. And from 1.8162, the graph goes from negative to positive. So our next objective would be to find the minimum and maximum values of velocity and acceleration.
The trick to understanding and answering these types of questions are pretty easy once you know what they're asking for.
You should know with your knowledge in finding maximum and minimum values that finding, for example, the maximum or minimum of s of t would require you to find its derivative, put it equal to 0, and solve for critical numbers t. Then find if the derivative of the numbers to the right or left of t are positive or negative. If it goes from positive to negative, there's a maximum value at that critical point. If it goes from negative to positive, there's a minimum value at that critical point.
Similarly, finding the minimum and maximum values of velocity and acceleration work the same way. To find minimum and maximum acceleration, you put a of t equal to 0, a prime of t equal to 0. To find maximum and minimum velocity, you put v prime of t equal to 0. And to find maximum and minimum position, you put s prime of t equal to 0. Another typical question regarding maximum and minimum asks for when a particle is farthest to the left or right. It is important to understand that when a particle is moving to the right, its velocity is positive, while when it moves to the left, its velocity is negative. So when it asks for the furthest to the right, you must solve for the maximum velocity, and when it asks for the furthest to the left, you solve for the minimum velocity. Here's an example.